So we're starting up with Chapter 2, which is motion along a straight line. So we're not going to be dealing with any kind of decomposition of vectors. That's going to be the next chapter. We're just going to establish the basic fundamental principles of motion in one dimension. Now the easiest way to start with this is with a number line, something that you guys should know a lot about from math class. So 1, 2, 3, minus 1, minus 2, minus 3. Now by convention, we say that on a number line, when you move to the right of the number line, we increase in the positive direction. When we move to the left on the number line, we increase in the negative direction. Now in physics, what we'll typically say is that to the right is considered the positive direction, or we will say that that is the positive direction east. And then if we move to the left, we're going to say that that's the negative direction, and that we are moving west. Okay? So the basic idea of the number line is going to help us. We can also do that along the vertical. We would say that movement up, the y-axis is positive, movement down is negative. Now then we get into this idea of displacement. And displacement is the type of term that is used incorrectly more often than it's used correctly. Displacement is a change in position. So when you change position, you are displacing. So right now I'm standing in front of you, I'm not moving, my displacement is 0. If, however, I take a step over to my left, your right, if I take a step over to my left, I have displaced some distance from my starting position. So displacement, delta x, stands for displacement. The Greek letter delta for change in x, x being our position. The change in position is equal to x final minus x initial. So if I start somewhere and I walk a step and then take a step backward, I started and stopped at the exact same point. So my displacement would be 0. Keep that in mind. Now, did I obviously travel some distance? Yes. But that's the difference between distance and displacement. Now, if I start at 1 on the number line and I move to 3 on the number line, my displacement is positive 2. I started at 3 for the final position, subtract the initial position, 1, so I have a displacement of positive 2. Notice that if I move in the other direction, if I start at 0 and go to negative 3, now I would have negative 3 minus 0. My displacement is negative 3, and that negative sign means that I was displacing to the left, or west. Now that's because displacement is a vector quantity. It has a number, and it has a direction. The positive or negative sign is what connotates the direction. Okay, now the idea of the average velocity. Average velocity is equal to our change in position over some time interval. So the average velocity, change in position over the change in time, or the time interval in question. This is not to be confused with instantaneous velocity, which is what we talked about on the calculus chapter a couple weeks ago. So keep that in mind. We will go into instantaneous velocity. So let's say that in an example for average velocity, we start at negative 3 meters, and we then move to 3 meters in 6 seconds. So we started at minus 3 on our number line, and we moved to 3 in 6 seconds. So we started minus 3, minus 2, minus 1, 0. 1, 2, 3. We started at minus 3, so this was our starting point, and then we ended over here at 3, that was our ending point. Our change in position, delta x, would be equal to x final minus x initial. Notice that x final is 3. We subtract the initial position, which is minus 3, to get a change in position of 6 meters. And that makes sense. We had to move right 6 units, and that is why we have a positive sign in front of the change in position. We did this in 6 seconds, so our average velocity is equal to the 6 meters divided by 6 seconds, or 1 meter per second. So our average velocity in this case was 1 meter per second. Hopefully that makes sense. Okay? And then if I think about a graph of position versus time, and here at 0 time we were at -1, -2, -3. We were -3 meters. And then 1, 2, 3, 4, 5, 6. 1, 2, 3. We're now up here at 3 meters in 6 seconds. If you find the slope of that line, you will get the average velocity. The rise over run is equal to 6 over 6, or 1 meter per second. So we got the average velocity either using the change in position over the change in time, or we graphed this thing and we looked at the slope. You should feel confident doing it either way. Either way you should feel confident. You should feel good about it. Now, average speed is something a little bit different. Average speed is something a little different. Average speed, so S average, the average speed, is equal to the total distance divided by the time interval. So notice it's not displacement in this case. It's not displacement in this case. Let's go back to this previous example. I start at -3, I go to 3 in 6 seconds. We got our average velocity to be 1 meter per second. My total distance traveled is also 6. But distance is not a vector quantity. The direction does not matter. So I moved 6 displacement, I also traveled 6 meters. However, if I start at -3, go to 3, and then come back to -3, my displacement now for the total trip is 0. I started and ended at -3. So my average velocity would be 0. My average speed, however, would be -3 to 3, I covered 6 meters, back again to -3, I covered another 6 meters, it would be 12 meters of distance traveled. So distance and displacement are used interchangeably, but they do not mean the same thing. Displacement is your change in position. Distance is how much you travel. Best way to think about it. When I was a kid, I always had to drive to Pittsburgh to see the rest of the family. Pittsburgh is about 300 miles away. So when I drive to Pittsburgh, my displacement was about 300 miles, my distance traveled was about 300 miles. If I come back from Pittsburgh to Philadelphia, my displacement is going to be 0. I stopped and started at my home. But my distance traveled would be the trip 2 times, so about 600 miles. Okay? Very easy to get screwed up on that, so be careful. And now, just to compare those two, if we say that we start at -3 meters, move to 3 meters, then to 0 in 6 seconds. So that means we went from -3 to 3 and then back to 0. The velocity average, the average velocity, would be equal to my total distance, my displacement, excuse me. I went here and then back to 0, so my displacement between the starting and ending points is 3. So that's going to be a 0 final position minus a -3 initial position divided by 6. So I get that my average velocity was 1/2 a meter per second in the positive x direction. So that's going to be east. I have to include some kind of direction on the displacement. Now my average velocity, however, and I'm sorry I'm going so low here, I apologize. The average velocity, I went from -3 to 3 and then to 0. So my total distance traveled is going to be 9. So 9 meters divided by 6 seconds. So that's equal to 1 1/2 meter per second. And we do not need to include a direction on the average speed. Speed is what's called a scalar quantity. And scalar quantities only have a number. They do not have a direction. You're either going to have a scalar or a vector. Scalar, just a number. Vector, number with a direction. Velocity is a vector. So notice I said 1/2 meter per second east. And now over here, if I was being real anal retentive, I should have said that that was 1 meter per second east. You want a direction on that velocity. Now, you could argue that the positive sign there means that you're traveling east, because at the very beginning of our conversation we said that any motion to the right on a number line is considered positive. That is okay too, but make sure then that if you have any motion to the left or west, you include a minus sign. Okay? Now we're going to move on into instantaneous velocity.